Hello and welcome to a new video in a course on linear algebra. In the previous videos, we introduced vector spaces, their properties, and we've talked about subspaces and their properties. In this video, we will be starting a new chapter where we will discuss linear transformation matrices and the properties of these. Now, when we study mathematical structures, usually we study maps between them because usually, for example, if you have two vector spaces, V and W, right? So we usually, in order to better understand the vector spaces, we usually study maps between these. Like we study maps between these vector spaces, and properties of this map can tell us something about the vector spaces. Now, now we don't want to take any function because remember, vector spaces are themselves sets with two operations, right? But in the first place they're sets, right? So we don't want to take any function f. If v and w were just sets, we would take f to be just a function, like just any function that would go from this as a domain to this as a codomain, right? However, since we're talking about sets with structure, like we're talking about vector spaces, like the vector space V has an addition and has a scalar multiplication, right? So we're talking about sets with structures. So it's better that it's like this map that we're considering better respects some of these structures, right? It better respects these because we're interested in properties of vector spaces, not properties of sets, right? So just to summarize what I'm trying to say here, I'm trying to say that the maps we're gonna consider between vector spaces are maps that respect the structure of the vector space, right? And these maps are called linear transformations. Talk about the notions of injectivity, surjectivity, and bijectivity, and we'll be also talking about the kernel and the image of the linear transformations. So let us get started. So let's say we have two vector spaces, v1 and v2, right? So we're starting with two vector spaces. Now, a linear transformation from v1 to v2 is defined to be a function. Well, it's a function between the sets to start with, because v1 is a set with two operations. I'm gonna call them +1 and +2 and dot 1, and then I'm gonna call those of v2, I'm gonna call them +2 sub 2 and dot sub 2, just to indicate that this addition corresponds to this vector space and this scalar multiplication corresponds to this vector space, and similarly for these operations, right? Because they need not be the same. For example, V1 can be the set of matrices where the addition and scalar multiplication are defined different from those of V2 that can be, for example, the real numbers, where addition and scalar multiplication can be just defined in the trivial way we define them for real numbers, right? So so a linear transformation between v1 and v2 is a function between v1 and v2 such that it respects the properties, it respects the structure of the vector spaces. In other words, if you add two vectors and take t of that, it should be the same as taking t of the first plus t of the second. In other words, t respects the addition of v1. In other words, like if you add two vectors and then map them, it's the same as mapping them and then adding them. I should note here that this addition is happening in v1 because these vectors, we're starting from vectors in the domain. So this is the domain and this is the codomain, right? So so this addition is happening, so this addition over here is happening between vectors in v1, right? And this addition over here is, this one is happening between vectors in v2 because t of v1 is gonna map v1 from here to t of v1, so it's gonna be an element in v2. So this is all to say that t should first of all respect the plus operation, and second, it also should respect the scalar multiplication operation, where if you have a vector, if you have a vector in V1 in the domain and you have a real number R, then T of RV, it should be the same as R times T of V, right? So you can pull the R outside. And I should note here that this scalar multiplication here is the dot one. It's the scalar multiplication of V1, because V is a vector in the domain which is V1, which is big V1. However, here over here on the right hand side we have T of V. This is a vector in V2, and the scalar multiplication, this one, it's gonna be and this scalar multiplication is a scalar multiplication where in V2, right? So this is what a linear transformation is. It is a function which respects the addition and scalar multiplication, and that's it. So you have two vector spaces, you want a map between these. The map has a certain property, which is that it respects the addition and scalar multiplication. And what do we call this map? We call it a linear transformation. That is it. So sometimes it's easier, just to save time, in order not to check two properties, you can check them at once. Like you can check that the two of these hold at the same time. That the two of these hold at the same time. In other words, here's an equivalent definition. Let V1 and V2 be vector spaces. T from V1 to V2 is a linear transformation if and only if T of V1 plus R V2, so these are vectors, is equal to T of V1 plus R T of V2. So this should happen for every V1 V2 in V1, in big V1, and for every real number R. So the linear transformation here, like it respects the addition, and it also respects the scalar multiplication, as you see, because we could pull the R outside. Now, just for practice, let us prove that this definition and this definition are equivalent. So let us call this definition 2, and let us call this definition 1. And let us claim that it's the same, like you can define it in either way. Let us claim that definition 1 is the same as definition 2. So it's equivalent to it. So here's a small proof, because it's an easy thing to show. So let us show the first direction. So we're supposing that we have a map T that satisfies 1 and 2, and we want to show that it satisfies this property. Well, what we do is that let V1, V2 be in V1, right? And R be in the real numbers. And we want to check that T of V1 plus R V2 is equal to the right-hand side. So we're assuming this, and we're trying to prove that. So T of V1 plus R V2, what is that? Well, if we use property 1, because we're assuming definition 1, if we use property 1, so this is by property 1, we have T of V1 plus T of R V2. Because if you consider this as a vector in V1, in big V1, and this is a vector in big V1, then we can apply this property that T respects the addition, and thus we can split this into 2, right, as such. Now, by property 2, what do we have? We have, this is the same as T of V1 plus R T of V2. And why is that? Because property 2 tells us that the T that we have respects the scalar multiplication. In other words, you can pull the constant outside. And that is it. I mean, this is what we wanted to prove. We wanted to prove that this equality holds, and we just did that. And this is happening for any V1, V2, because we started with generic ones. Let us prove the other way around. This is an easy proof. Let us do it. So we're assuming this thing, and we want to prove that the map should satisfy property 1 and property 2. So let us prove that. Well, so let v1, v2, and r be in R. So let this be in v1 and let r be in R. And we want to check property 1. We want to check that t of v1 plus v2 is equal to t of v1 plus t of v2. So this is what we want to check. Now, so why is this true? Well, we know that this property holds. So let us call this property star, right? So we know that this property holds. And what we can do is that we can take the number r to be 1, right? If we take r to be 1, what happens is that this equation star, it reduces to this thing that we want to prove, right? So plug r equals 1 in star to get the above equation. If you just replace r by 1 here and here, and you remember that scalar multiplication by 1 gives the same vector back. So this is one of the axioms of defining what a vector space is. Okay, so scalar multiplication by 1 gives the vector back. So star reduces to this equation. The property 2 that we want to show is that we want to check that t of r v1 is equal to rt of v1. So this is what we want to check. Well, why is this true, or how can we get this? Well, here's how you can get this, and this is an important thing to keep in mind. So let us see this real quick. So if we take, what happens if we take v1 to be 0, right? If we take v1 to be 0, let's see what happens. So this is the equation that we have. Look at it, and I'm gonna just copy it below and replace v1 by 0. So if I copy it below and replace v1 by 0 by star, taking v1 equals 0, and just to be clear here, just to follow the notation, let's ask ourselves to prove this. We want to prove this, okay? So because it doesn't matter, we're starting with any vector v1 and any vector v2. It doesn't matter, just to stick to the notation. So by star, we have t of 0 plus r v2 is equal to t of 0 plus r t of v2. Now this left hand side, this is equal to t of r v2, excuse me. Why is that? Because 0 is the identity, or the additive identity. Now on the right hand side, I claim that this is equal to 0 plus r t of v1, t of v2. And thus this is equal by the fact that 0 is an additive identity. This is equal to t of this is equal to rt of v2, and this proves what we wanted. This proves that this left hand side is equal to this right hand side. However, there's something to prove here. Why is t of 0 equal to 0? So why? This is something that we need to show. So to show this, it's an easy thing to show. So let us just do it as a separate proposition. So let us just finish this here. Let's say that this is done if we prove that t of 0 is equal to 0, right? So let me show you now. Why t of 0 is 0. So here's a proposition for you. Given two vector spaces, v1 and v2, and let t from v1 to v2 be a linear transformation. So we know that T is a linear transformation, which means it satisfies the definition 1 that we gave, right? So what we want to show now, we want to show that T of 0, then T of 0 is equal to 0. And but this 0, I should stress here, this 0 is in V1. This is the 0 of V1 because it's the 0 of the domain. And the 0 is in V2. This is the 0 of the codomain, right? So let us see why this is the case. So here's a quick proof for that. Well, so by property 2, we have T of RV is equal to RT of V for every V in V1 and R in R in the real numbers. So property 2, from the first definition that we gave, it says that the linear transformation, by definition, it respects scalar multiplication. You can take the scalar outside. So this is what I'm saying here. By property 2, this is what we have. Now, here's a trick. Now let's take R to be 0, right? So take any V in V1, and take R to be 0. What do we have? We have T of 0 dot V is equal to 0 dot T of V. Now I just want you to be careful here. This is a vector and this is a number, because remember, it's scalar multiplication, and this is also a number, right? So we know by a previous proposition that we proved in a previous video that 0 times any vector gives 0 back, gives the vector 0 back. So this thing is just T of 0, and this right hand side is just 0 because also it's 0 times a vector, and thus it's 0. However, I should mention here that this 0 is the 0 of V1, and this 0 is the 0 of V2. This is the 0, these are the zeros vector, right? These are the 0 vectors, right? So so this is what we have. This is what we wanted to prove. We wanted to prove that T of 0 is 0, and this is what we got. And this completes also the proof of this thingy over here. So this first proposition, it's important to keep in mind. And the second proposition is also, so the first proposition that we proved, which is that the definition 1 and 2 are the same, is important because when you want to check or you want to prove that a linear transformation or a map is a linear transformation, it's enough to check one thing. It's enough to check this instead of you having to write 2 checks for this thing. Though it's not a big deal here. So the other important proposition that we proved is that if you have a linear transformation T, then T of 0 is 0. And this is very, very important. And we're going to see how important is this as we go in the lectures. So this is the second thing that I wanted to prove. So let us go ahead now and talk about injectivity, surjectivity, the kernel, and the image of a linear transformation. Alright, so now that we've defined what a linear transformation is, let me just give you a few examples. Let us go over these one by one. So perhaps I should write the definition here for you, just to remind you here. So let V1, V2 be vector spaces. Let T between V1, okay, so T between V1 and V2 is a linear transformation if and only if T of V1 plus R V2 is equal to T of V1 plus R T of V2, and this is happening for every real number R and V1, V2 vectors in the domain, which is big V1. So this is the definition of what a linear transformation is. So let us see now why these examples are linear transformations. So let's start with the first one. So some of these terminologies are important for you to keep in mind. These will be showing up later in the course. So first of all, the zero transformation. Important name to keep in mind. right? The zero transformation, it's a linear transformation that takes every vector to zero, right? So let us write here why it is a linear transformation. So let's say we have v1. So let me just say here, generally, let's say we have v1 v2 vector spaces, and the first example, t from v1 to v2, is defined as t of v is equal to 0 for every v in the domain, right? And this zero is the zero vector, and it's since t of v is in v2, is in the codomain, this is the zero vector of v2, right? Of the vector space v2. All right, so this is, we're claiming that this is a linear transformation. Why is this the case? I hope that this is clear. This is an easy thing. So let us check this using the definition here real quick. Well, t of v1 plus r v2, right? This is what? So we're also starting, let v1 v2 be in the domain, and r be in R, be a real number. So want to prove that property star holds, right? How do we prove this? Well, t of v1 plus r v2 is equal to what? Well, this is a vector in v1, and the definition of t is that it takes any vector to 0, so this is just 0, right? Similarly, if you look at t of v1 plus r t of v2, like the right hand side of property star, you see that this first thing is 0 by the definition, plus r, this thing is also 0 by the definition. But if you scale the 0 vector by a real number, you also get 0. So this is 0 plus 0, and thus the answer is 0. And thus this thing and this thing are equal, and thus property star holds, which makes this a linear transformation. So let's see why the second example is a linear transformation. It's important also to keep this name in mind. It's the identity transformation. And what this transformation does is that it takes any vector to the vector itself. Like, it doesn't do anything to the vector. It just takes the vector and gives you the vector back. So let us see what we mean here. We mean that if we have this linear transformation from v1 to v2 from these two vector spaces, and we're defining t of v to be v for every v in the domain. This is what we have. Now we want to check property star, but this is clear, so let us see why it's clear. We want to check that t of v1 plus r v2 is the same as when you distribute the t's, right? When you distribute the t to the v's, right? So let us see why this is the case. By definition, so this thing is equal to whatever is inside the parentheses. This is the definition of t. So it keeps the input the same. And then on the other hand, if we look at the other thing, the other part of the property, we have t of v1 plus r t of v2. What is that? Well, this is by definition is equal to v1 plus the r is the same, and this by the definition is equal to v2. And these two are equal, and thus this and this are equal, which makes property star satisfied, and thus this transformation, which we usually denote by I, is so probably I should have written this as I just to be consistent. This is actually a linear transformation. So let us take another example. So the other example that we want to take is a transformation from R2 to R3, right? So I wanna remind you here. We proved previously that Euclidean spaces are vector spaces, right? So we proved previously that R to the n, when equipped with addition, so we proved in a previous video that Rn, when equipped with the element-wise addition and scalar multiplication, this is a vector space. So we have two vector spaces here. So when we define a map and we ask whether it's a linear transformation or not, this is a legitimate question because these are actually vector spaces. So let us see why this is the case. Why is this map a linear transformation? Well, I don't want to write details here because it's kind of getting messy, but let me just show you why it is the case, right? Let me just show you why it is the case. So if we take this map from V1 to V2, where we're defining T of x1, x2, excuse me here, V1 here is R2 and V2 here is R3. So we're defining T of x1, x2 to be 2x1 minus 3x2, 3x1 plus 4x2, and 5x1 plus x2. So this is what we're defining, right? So we want to check property star. We want to check that this property holds, right? And as you see here, the input is a tuple, is a tuple of size 2. Like we have 1, 2 components. In the output is an R3, and thus it has 3 components, 1, 2, 3. So in this case, checking property star can be a little bit tedious. So I'd rather check properties 1 and 2 from the other definition. So I'll check separately that T respects addition and scalar multiplication separately, right? So in this case, it's easier to do this. So if we start with any, so let us start with x1, x2, let's say y1, y2, these are in R2 and a real number R. So so if we add these two, adding these two is the same as taking T of x1 plus, excuse me, this should be y1 and this should be y2. Okay, it should be the same as T of x1 plus y1, x2 plus y2, right? Because this is how we're defining the plus in R2. We're defining it element-wise or component-wise. Now, if you substitute back in the definition of T, you see that you get T of the first component, which is x1 plus y1, minus 3 times the second component, which is x2 plus y2. And you get, similarly, you just plug in things in the definition here. So you get, for the second component, you get 3x, you get 3 times the first component, x1 plus y1, plus 4 times the second component, x2 plus y2. And for the last component, you get 5 times the first component, plus 3 times, no 3, plus the second component. So this is what we have. So you see here, if you just distribute this, if you just distribute these things, what do you get? Well, you get 2 times x1, and from here you get minus 3 times x2, right? So let us write this. We get 2 times x1 minus 3 times x2. So we should close this here. Okay, so I'm gonna put a comma here, I'm gonna put a plus here. I'm gonna show you what I mean. So if you remember, in R3, we also have the addition defined component-wise. So you can separate the components into 2 tuples, into 3 tuples, right? So if you look closely, you will see that this first thing is T of x1, x2. Look at the definition here. Look how this is defined. And if you look closely at this one, you see that this is T of y1, y2, right? So we just proved that T of the sum is the sum of the T's. And this is the property 1 that we wanted to show. And I'm gonna leave it as an exercise for you. So exercise, check that T of R x1, x2 is equal to R times t of x1 x2. And what you're gonna use here is that you're gonna use that this thing is the same as rx1 comma rx2, because this is how we're defining the scalar multiplication in R2. And similarly, you use similar things in R3. So I'm gonna leave it as an exercise for you to check this. So the fourth example we want to go over is this thing. If you take if you take the linear transformation to be a scaling linear transformation, in other words, it takes any vector and it scales it by a constant, right? So let's take this and let's prove it before we go to the next topic that we want to talk about. So so let's take the fourth example. Okay, so let's take t from v1 to v2. And let's define it by t of v to be defined as 2 times t of v, times v, excuse me. So what we're gonna do is that we're gonna define t to be a scaling linear transformation, which means it takes the vector and it just scales it by a number. In this case, I chose the number to be 2, but it doesn't matter. You can choose any real number. And I wanna just turn your attention to something, that if you consider the scaling linear transformation and you take this constant to be 0, what happens is that the output will always be 0, because 0 dot any vector is 0, and thus you get the 0 linear transformation that we talked about in example 1. You get this thing, right? So this thing is a special case of this thing when a is 0, right? So let us just prove this. Prove that this is a linear transformation. Well, this is also easy to show. So let us just check property star. So we want to check that t of v1 plus r v2 is equal to t of v1 plus r t of v2. So we're gonna set r real number and v1 v2 to be vectors in the domain, and we're gonna check this. So, well, we're gonna start by this left-hand side. What is that? This is whatever is inside by definition, we hit it by 2. So it's gonna be 2 times v1 plus r v2. Since real numbers are commutative over multiplication, you can swap these two and rewrite the term as 2v1 plus r times 2v2. So in this case, we used distributivity again, and we used the fact that we can swap these two numbers. And thus, this whole thing is gonna be, now by definition, look at the definition here. By definition, the first thing is t of v1 plus r. The second thing over here is what? Is t of v2, because this is what t is defined to be, right? And we just proved that this left-hand side is equal to this right-hand side, which proves that t is a linear transformation. So this proves that t is a linear transformation.